thank you for the introduction. And first of all, I'd like to thank organizers for the chance to present our recent work on FMQA that is introduced in the previous presentation. And in this work, we improved the performance of FMQA by using the round starting method. Okay. This is the goal and outline of my advantage of FM initialization method with low-rank approximation, which will be introduced later, over the random initialization method, which is usually used in the machine learning field. And to this end, I start with introduction of the background of this research. In the background section, I'd like to explain what is a black box combinatorial optimization program, and at the last of this section, I'd like to explain the motivation of our study. And the next topic is the round starting FMA. In this section, I'd like to introduce the initialization method with low-rank approximation and the random initialization methods. And in the next section, I will compare these initialization method and show the advantage of the initialization method with low-rank approximations. Okay, let me start with the background. Well, first of all, I'd like to explain the requirements for the optimization with quantum annealing machines. In order to use annealing machines to solve combinatorial optimization problems, we need to formulate cost function in the cube form for Ising model like this. Here, C and QII and QIJ represent some real number, and XI is 0 or 1 for Q model, and Xi is 1 minus 1 or 1 for Ising model. The task of combinatorial optimization is to minimize this value by changing the input variables. But the question here is that is it possible to represent any cost function of combinatorial optimization in this cube form? And as you know, many combinatorial optimization problems can be expressed in this cube form, but not all combinatorial optimization problems can be expressed in this form. In particular, black box optimization problems cannot be formulated in this cube form. Okay, what is a black box optimization problems? Black box function is some kind of function, but we do not know the analytical form of the function. In other words, there are no we don't know the explicit form of this function. But if we input some value into the black box function, we can get some output. So by calling black box function, sometimes we can obtain some input and output relationships like this. And the task of black box optimization is to minimize this black box function. In other words, to find the input variable that minimize this output of this black box function. Well, typical approach to black box optimization problem is called model-based optimization method. Again, black box function is expected form to evaluate black box functions. So we cannot search optimal solution by calling black box function many times. In the model-based optimization method, instead of deal with black box function itself, we construct a surrogate model that reproduce the input and output relationship of black box function. And we try to minimize this surrogate model instead of black box function. This is the surrogate model-based optimization method. FMQA or FMA is a kind of such an optimization method. In the FMA, factorization machine is used as a surrogate model. Factorization machine is given by this equation or this equation. There are two kinds of factorization machine based on the sign in front of each factors, but I will explain a bit differently. Okay, let's focus on the positive factorization machine. There are three terms: constant term, and linear term, and interaction term. W0 and W0 is a constant, and Wi is some real value, and Di is a k-dimensional real vector, and Di times Dj represent here is inner product of these two vectors, and Xi is the variance. The task of factorization machine is to reproduce the input and output relation of black box function. To achieve this, we use a machine learning technique. By tuning these model parameters W0, Wi, and real vector, we can train this model so that input to this positive FM is equal to the output of the black box functions. The benefit or the advantage of this factorization machine is the following. First, modification is quadratic form, so we can find the minimum. We can minimize this function by using the quantum annealer or symmetric annealer. The next point is the time complexity for the forward calculation is linear as given this equation. K is the input. K is the dimension of this vector, and n is the input dimension. So calculation is very fast. The last advantage is the time complexity for training. Also, in the training, the time complexity is given by this equation, so training is also fast. We have already applied FMA to various problems, and we obtained many fruitful results. For example, this is the original paper by Kitai-san that is in which FMQA is proposed. They apply FMQA to optimize the design of the metamaterials. And in this case, we are trying to optimize the structure of photonic crystal laser to maximize the performance of the lasers. As you can see, we can apply FMQA with various type of problems, and this is a advantage of FMQA. Optimal solutions. There are 4 steps, and there are 4 steps. In the first steps, we need to prepare the initial training dataset by calling black box function sometimes. In the next step, we train the factorization machine using the obtained dataset by using a propagation method. Then we can obtain the factorization machine that reproduces this training dataset. In the third step, we try to minimize the factorization machine by using annealers and obtain the new samples. In the fourth step, that obtains samples, we add these new samples to do this training dataset, and so the number of data points in the training dataset increases as we repeat this sequence many times. So after the sufficient number of data points is obtained, the accuracy of factorization machine becomes very high, and then we can find the true ground state of black box function by solving the machines. FMQA or FMA can be considered as one of the quantum classical hybrid methods using accelerators. If we use the quantum annealer for annealing machine. The two main technology in FMA is annealing machine and machine learning. In the machine learning, we can use the GPU to accelerate the calculation, and in the phase of finding the samples, we can use an annealing machine to accelerate the calculations. So we can combine these two accelerators to minimize the total computational time. Okay, before going to the more detailed calculation, I will show the very simple demonstration of FMA. In this demonstration, we are trying to solve traveling salesperson problem, TSP. As you know, the task of TSP is to find the shortest path that goes through all the points and go back to the original position. The task of factorization machine is to reproduce the projected functions, and here shows the interaction value of interaction matrix by using a color. And TSP is a very simple program. We know that two interaction matrices like this, but in the beginning of the calculation, we don't know the actual interaction. So interaction matrix is initialized randomly like this. And when we start the FMQA calculations, the number of dataset increases, then the accuracy of the factorization machine increases, and it converts to the true state. After that, by sampling the ground state by using annealer, we can find the best solution like this, and the cost function is decreases like this. So this demonstration shows that FMQA works as expected. Okay. Okay, let's move on to the motivation of our research. In some cases, as an Ising model that approximates the research and it is research. In this case, black box is not a true black box, but we have a small information of black box function like this. And we try to consider the task that to obtain approximate represent this obtained approximate function using a factorization machine. In other words, which value should be used as this model parameter. So to solve this program or questions, I'm going to move on to the next part. In this part, I'd like to introduce a new idea when starting FMA. In the one starting FMA, it is assumed that approximate interaction matrix is for the black box function is given, and we'd like to initialize the factorization machine that reproduce these approximate interactions. Then we start this warm static state as the initial state of FMQA, and under FMA iterations, normal FMA iterations, and increase accuracy of factorization models. This is the basic idea of FMA, and this part is called one-starting initialization, and this is the main target of this talk. And the result is already uploaded to the archive. So if you are interested in, please visit this archive. I will show this archive number again in the summary. Okay, we consider two types of initialization method. First, we consider initialization with low rank approximations. So in this low rank approximation method, the interaction parameters of the factorization machine can be determined by using low rank approximation of coupling matrix J, which is given by as an approximate interaction matrix. First, we derive the eigendecomposition of this matrix J like this. Here, sigma represents the diagonal matrix with eigenvalues, and U is some unitary matrix to diagonalize the matrix J. In order to make this matrix to semi-positive definite, we use the parameter eigenvalue shift, and we obtain the new new interaction matrix J prime, which is positive definite, and the eigenvalues is represented by like this. And if we choose the shift value as the minimum smallest eigenvalues, the smallest eigenvalue after the shift can be 0. And we preserve the higher k dot k eigenvalues like this, and we can approximate this new interaction matrix J prime like this. Here, sigma k prime is given by this k-dimensional diagonal matrix, and UK is unitary matrix that has corresponding eigenvectors for remaining eigenvalues. By using these equations, we can initialize of the factorization machine like this. And by using this model parameter as an initial model parameters, we can approximate the original interaction matrix by using a factorization machine. Another initialization method is random initialization. This is a common method used in machine learning field. In our study, we consider two types of random initialization method. First, initialization method based on the energy distribution of the target black box function. The second is the initialization method based on the interaction coefficient distribution of the target interaction matrix. In the initialization method based on energy distribution is obtained as follows. First, we prepare the energy distribution for the target approximated Eigen model by assuming the high temperature limit. Then we try to find the factorization machine whose energy mean is equal to that of the approximated Eigen model, and the variance of the energy distribution is equal to that of the approximated Eigen model. Calculation is not so difficult and straightforward, and we obtain that if we choose the model parameter 3ij like this, and it's a Gaussian distribution with zero mean, and variance is given by these equations. Then the energy distribution of factorization machine is almost identical to the energy distribution of approximated Eigen model. In the second method, initialization method based on the coupling distribution, we can calculate in a similar way, and we can find that VIK should follow this Gaussian distribution. Here, this is mean value is given by mu over k, square root of mu over k. Here, mu is the mean of the coupling constant J prime, and variance is given by this. Here, and sigma squared represent variance of the coupling constant distribution of J prime. If we choose indicate by using these equations, coupling constant of factorization machine has a similar property as that of the approximated eigenmodel. Okay, this is a setup. We know the black box function and approximately like this SK model functions. And the performance indicator is the coupling error defined by this. ELG is the coupling constant of SK model, and G is the coupling matrix estimated through the training of SK model using the initialization method mentioned before. Here is the first result. This is the comparison between the random and negative percent. And the last one has a very low errors. So in the random initialization method, this initialization method is the best. Next week, I'd like to compare. Okay, so this is the last slide. I'd like to compare the low rank approximation method with the random energy method. And this video shows that low rank approximation method for the negative FM has the best performance. Okay, this is the summary, but I don't have enough time. I thank you very much.
My apologies for the imposition. I think we have time for like one quick question. Okay, maybe very quickly. With the initialization, the low rank matrix, I'm not quite seeing why this would be a good initialization. Can you elaborate a little bit why people started doing this in the first place?
The reason why initialization, sorry, but which part of the site which part?
Yeah, but basically, like it seems like the low rank initialization seems to be useful to, or seems to be a good initialization, right?
Yeah.
But it's not like I'm making a picture of why that would be the case, like theoretically. So.
But I have an answer right now, so
no, that's fair. Yeah, well then let's applaud once more for Yuya.